Hi, and welcome back. In this course, you've learned about object recognition, where the goal is to input a picture and figure out what is in the picture, such as, is this a cat or not? You've learned about object detection, where the goal is to further put a bounding box around the object is found. In this video, you learn about a set of algorithms that's even one step more sophisticated, which is semantic segmentation, where the goal is to draw a careful outline around the object that is detected so that you know exactly which pixels belong to the object and which pixels don't. This type of algorithm, semantic segmentation, is useful for many commercial applications as well today. Let's dive in. So, what is semantic segmentation? Let's say you're building a self-driving car and you see an input image like this, and you like to detect the position of the other cars. If you use an object detection algorithm, the goal may be to draw bounding boxes like these around the other vehicles. This might be good enough for a self-driving car, but if you want your learning algorithm to figure out what is every single pixel in this image, then you may use a semantic segmentation algorithm whose goal is to output this, where, for example, rather than detecting the road and trying to draw a bounding box around the road, which isn't going to be that useful, with semantic segmentation, the algorithm attempts to label every single pixel as, is this drivable road or not, indicated by the dark green there. One of the uses of semantic segmentation is that it is used by some self-driving car teams to figure out exactly which pixels are safe to drive over because they represent a drivable surface. Let's look at some other applications. These are a couple of images from research papers by Novikov et al. And by Dong et al. In medical imaging, given a chest X-ray, you may want to diagnose if someone has a certain condition. But what may be even more helpful to doctors is if you can segment out in the image exactly which pixels correspond to certain parts of the patient's anatomy. In the image on the left, the lungs, the heart, and the clavicle, so the collarbones, are segmented out using different colors. This segmentation can make it easier to spot irregularities and diagnose serious diseases, and also help surgeons with planning out surgeries. In this example, a brain MRI scan is used for brain tumor detection. Manually segmenting out this tumor is very time-consuming and laborious. But if a learning algorithm can segment out the tumor automatically, this saves radiologists a lot of time, and this is a useful input as well for surgical planning. The algorithm used to generate this result is an algorithm called UNet, which you learn about in the remainder of this video. Let's dig into what semantic segmentation actually does. For the sake of simplicity, let's use the example of segmenting out a car from some background. Let's say, for now, that the only thing you care about is segmenting out the car in this image. In that case, you may decide to have two class labels, one for car and 0 for not car. In this case, the job of the segmentation algorithm, of the UNet algorithm, will be to output either 1 or 0 for every single pixel in this image, where a pixel should be labeled 1 if it's part of the car, and labeled 0 if it's not part of the car. Alternatively, if you want to segment this image a little bit more finely, you may decide that you want to label the car 1. Maybe you also want to know where the buildings are, in which case you would have a second class, class 2, the building, and then finally the ground or the road, class 3, in which case the job of the learning algorithm will be to label every pixel as follows instead. And so taking the per pixel labels and shifting it to the right, this is the output that we would like to train a UNet to be able to give. So this is a lot of outputs. Instead of just giving a single class label, or maybe a class label and the coordinates needed to specify a bounding box, the neural network, UNet in this case, has to generate a whole matrix of labels. So what's the right neural network architecture to do that? Let's start with the object recognition neural network architecture that you're familiar with, and let's figure out how to modify this in order to make this neural network output a whole matrix of class labels. Here's a familiar convolutional neural network architecture where you input an image, which is fed forward through multiple layers in order to generate a class label y hat. In order to change this architecture into a semantic segmentation architecture, let's get rid of the last few layers. And one key step of semantic segmentation is that whereas the dimensions of the image have been generally getting smaller as we go from left to right, it now needs to get bigger so they can gradually blow it back up to a full-size image, which is the size you want for the output. So specifically, this is what a UNet architecture looks like. As we go deeper into the UNet, the height and width will go back up while the number of channels will decrease. So the UNet architecture looks like this until eventually you get your segmentation map of the cat. Now, one operation we had not yet covered is what does this look like to make the image bigger? To explain how that works, you have to know how to implement a transpose convolution. So that's semantic segmentation, a very useful algorithm for many computer vision applications, and where the key idea is you have to take every single pixel and label every single pixel individually with the appropriate class label. As you've seen in this video, a key step to do that is to be able to take a small set of activations and to blow it up to a bigger set of activations. In order to do that, you have to implement something called the transpose convolution, which is an important operation that is used multiple times in the UNet architecture. So let's go on to the next video where you learn about the transpose convolution. I'll see you in the next video.